So waves are disturbances that carry energy but not matter. So I want you to have a picture in your head, not of waves breaking on the beach, but deep out to sea where the waves are rhythmically going up and down, up and down, up and down. That's the picture you need to have. Now there's a couple of different ways to classify waves. We can classify waves as mechanical waves. Mechanical waves are those that need a medium to travel through. So sound waves are an example of a mechanical wave. Let's have a look at this clip from PhysClips now, showing what happens when we remove the medium that sound waves need to travel through. Sound waves need air to travel through.
Travels from the source to our ears, passing through air on the way. Let's pump the air out of the jar. The sound level is much reduced. Some vibration is conducted through the floor of the jar, but there's no air to conduct sound. Until we let the air back in.
So this means that all those space movies, such as Star Wars, where the spaceship explodes and then there's this massive bang, are all wrong. In space, there's no air, it's a vacuum, and so sound doesn't actually travel. Other examples of mechanical waves include water waves, waves sent along a string or a spring, and waves generated in an earthquake. Now the other type of wave is an electromagnetic waves. Electromagnetic waves are waves like light waves, radio waves, X-rays, gamma rays. These waves all travel through space at the speed of light and do not require a medium to travel through. They only travel in a vacuum in the speed of light. When they enter another medium, they actually slow down, as we'll see in the next topic. So this image shows you the different parts of the electromagnetic spectrum. Speed cameras use a wavelength of about 3 centimeters, so this falls just into the radio wavelength. So waves are periodic disturbances. This means that the pattern of a wave repeats itself. So now let's look at another way to classify waves. Waves can be classified as transverse or longitudinal. In a transverse wave, the particles which make up the medium move in a direction which is perpendicular to the direction the wave travels. So let's have a look at this example from PhysClips showing a transverse wave moving along a slinky coil.
So here you see the actual particles making up the slinky move up and down while the wave travels from the left to the right.
So examples of transverse wave include waves on a string or electromagnetic waves. In electromagnetic waves, it's actually the electric and magnetic fields oscillating in a direction perpendicular to the direction the wave is traveling. The other type of wave is a longitudinal wave. In a longitudinal wave, the velocity of the wave is parallel to the direction that the particles that make up the medium vibrate. So examples of longitudinal waves include sound waves and compressions sent along a slinky coil. So let's now have a look at this example of a longitudinal wave, again taken from the PhysClips site.
So in this clip you can see that with the longitudinal wave, the particles making up the slinky move in a direction parallel to the direction that the wave travels.
Now there's several terms associated with waves that you're going to need to know. First of these is wavelength. The wavelength, like its name implies, is the length of the wave. It's given the symbol lambda and is measured in meters. So one way to measure the wavelength is to measure from the crest of one wave to the crest to the next crest on the wave, and that difference in distance is called the wavelength. Alternatively, you could measure from the trough to the trough. The amplitude of the wave is half of the height between the crest and the trough. So the amplitude is actually the maximum distance that the particles can be from their equilibrium position. So amplitude is generally given the symbol capital A and is also measured in meters. The period of a wave is given the symbol capital T. To measure the period of the wave, you'd measure, if you started your stopwatch when one crest passed you and then waited until the next crest passed you, you would have measured one period. So the period is how long it takes for one wavelength to move past you. The period is measured in seconds. The frequency of the wave is the inverse of the period. So it's how often these crests pass you. The units for the frequency are hertz or inverse second. So frequency is given the symbol F, and the frequency is equal to 1 over T. So let's do an example now.
So the question is, a wave travelling in the positive x direction is pictured below. Calculate the period, frequency, amplitude and wavelength if you measure that it takes 2 seconds from when one crest passes you until the next crest passes you. And here's the diagram showing the wave. Okay, so we know that the period is equal to 2 seconds, as it takes 2 seconds from when one crest passes you to when the next crest passes you. So the frequency is equal to 1 over the period, so that's 1 over 2, which is equal to 0.50 hertz. The wavelength is equal to the distance between the two crests, so that's 40 centimeters, which is 0.40 meters. And the amplitude is the displacement from equilibrium, so that's this 20 centimeters. So the amplitude's 20 centimeters, which is 0.20 meters.
Now, one important thing about a wave is its speed. The speed of a wave is just given by the frequency times the wavelength. Now, this isn't too hard to derive, as we know that speed is equal to distance over time. So the distance that a wave has to travel to be back to where it started from is 1 wavelength, and the time it takes to do so is 1 period. So we have that the speed is equal to 1 wavelength divided by 1 period. Now the inverse of a period is just the frequency. So this leads us to V is equal to F lambda. The velocity of the wave is equal to the wavelength times the frequency. Let's do an example now where we'll work out the speed of a wave.
So the question is, given the same wave as before with a period of 2 seconds, calculate the wave speed. So in order to calculate this, we'll need to use V is equal to F lambda. So we know that frequency is equal to the inverse of the period. So this is the wavelength over the period. The wavelength is the 40 centimeters, so 0.40 meters, and this is divided by 2.0. So we get 0.20 meters per second, or 20 centimeters per second.